We're going to take some time right now to talk about the basics of probability. Some of you might be intimidated by the math associated with finding probability. However, there are just a few rules concerning probability that you'll need to know for this course, and we're going to discuss these rules now. Beyond just these basic rules, it's just important to know that probability is sort of working behind the scenes in statistics. Right now, it might not be clear what probability has to do with making decisions based on a set of numbers, but that will become more clear throughout the semester. Probability is basically looking at a target outcome and evaluating its likelihood of occurrence against all other possible outcomes. So if you want to look at the probability, for example, of rolling 6 on a die, we need to look at all the other possibilities, 1, 2, 3, 4, and 5. Another definition of probability is the likelihood of the occurrence of an event. These are both saying the same thing. How likely is something to happen? And we do that by comparing the chances of that event happening versus all other alternatives. And the really wonderful thing about probability is we can predict the future based on the past. If we know how many times something has happened before, we can figure out the likelihood or probability of it happening again. If 90% of a salesperson's cold calls result in a hang-up, then there's a 90% chance the salesperson will get hung up on in the next call. Such a bummer. Probability is a central idea in statistics in that it helps us to understand sampling error. We're going to talk more about samples and populations next week, but we conduct studies on samples, which are actually subsets of a larger population. Very rarely do we have the ability to study the full population in which we're interested, such as American teenagers or prisoners over the age of 50. Instead, we study a representative sample of a larger population, and we generalize what we found in the sample to be true of the larger population. So when we draw from a sample, we're not getting a perfect measure of something because in reality, we're interested in the full population. But probability helps us figure out how likely the sample represents the population group that we're really interested in. So while some of these examples of probability might not seem useful to you right now, for example, you might not be wildly interested in the probability of drawing a king of hearts from a deck of cards, unless you like to gamble. Probability does help us with statistics, which enables us to answer research questions. So to reiterate, the formula for probability is the number of times an outcome or an event can occur divided by the total number of times any outcome or event can occur. There is only one number 6 on a die, and there are 6 total possible numbers on a die. But knowing the numbers 1 and 6, I can figure out the probability of rolling a 6. So let's go through some rules of probability. One rule of probability is that probabilities range from 0 to 1. A probability of 0 means there's 0 chance of an event occurring, and a probability of 1 means something occurring is completely certain. The probability of being struck by lightning or winning the lottery is closer to 0. The probability of laughing during an episode of Modern Family is much higher. Most probabilities range between 0 and 1. The converse rule of probability is actually a rule regarding the probability of something not happening. I know that the probability of rolling a 6 on a die is 0.17 because there's one possibility out of 6. 1 divided by 6 is 0.17. So what is the probability that I will not roll a 6? The converse rule of probability uses the formula 1 minus the probability. So 1 minus 0.17 equals 0.83. There is a probability of 0.83 that I will not roll a 6. If that doesn't roll off the tongue so easy, you can say that there's an 83% chance of not rolling a 6. And you'll see very easily that the probability of something happening plus the probability of something not happening equals 1. The next rule of probability is the addition rule, which states that the probability of obtaining any one of several distinct outcomes equals the sum of their separate probabilities. Here is the formula for the addition rule. The probability of A or B is equal to the probability of A plus the probability of B. We use the addition rule when we are interested in the occurrence of A or B. The key word for using the addition rule is or. We can sum these possibilities to find the overall probability of at least one of these things happening. Let's use an example from a deck of cards. Well, as you know, a deck of cards has 52 cards, and in a standard deck of cards, there are 4 kings and 4 aces. What is the probability of choosing a king or an ace? Well, first we need to determine the probabilities for each. So the probability for drawing a king, 4 out of 52 cards, or 0.08, and the probability of drawing the ace is going to be the same because there are 4 ace cards as well. To find the probability of a king or an ace, I simply add 0.08 plus 0.08 to get a probability of 0.16. It makes sense that the probability of getting a king or an ace would be higher than each of the individual probabilities, right? If I found out a deck of cards on the table, and believe me, I can do it, having 4 kings and 4 aces to draw from, or 8 cards total, results in a higher probability than if I was just drawing 4 kings over here or 4 aces over there. The word or increases the probability. When you add positive numbers, your answer will always be greater than the individual numbers. The word or opens up more options. So when you see the word or, that's a tip-off that the addition rule will apply. Very briefly, I mentioned that the addition rule applies with distinct or mutually exclusive outcomes. But what if I asked you for the probability of drawing a drawing a king or a hearts card? We know the probability for the king, 0.08, and a quarter of the cards in a standard deck are hearts, so that probability is 0.25. I can just add up those to find the probability of drawing a king or a hearts card, right? Well, no. The categories of king and hearts are not mutually exclusive, since there is one king card that is also a hearts card. So we have to employ a rule to adjust for what we call joint occurrences. We have to subtract out the possibility of a joint occurrence happening. The probability of drawing a king card plus the probability of drawing a hearts card minus the probability of drawing the king of hearts gives us a probability of 0.31 for drawing a king or a hearts card. You're not likely to encounter this in any of your work, but I just thought I'd mention it so that you have a sense of the addition rule and how it works with mutually exclusive categories. Okay, another important probability rule that you will be using is the multiplication rule. An example of when you might use the multiplication rule is if you were looking for the probability of getting a king and an ace. Perhaps we're playing blackjack, I don't know. So this time we're looking at the word and instead of or. So we already know the probability of getting a king is 0.08, and the probability of getting an ace is the same, 0.08. To find out the probability of getting both cards together, blackjack, we multiply 0.08 and 0.08 to get 0.006. Notice this time our probability is lower with these two cards being drawn together, and that just makes sense. It would be rarer to pull a king and an ace in combination rather than just a king or just an ace. So the word and sort of raises the stakes, raises the difficulty, and tips us off that what we will be using is the multiplication rule. When you multiply anything by a decimal under 1, your answer will be smaller. In other words, the probability is going to be less. Let's do an example together. Be prepared to pause your computer at the end to work out the probability question. Returning to our mythical salesperson, we'll call her Betty. Betty wants to contact doctors via email in one city, and she uses an internet listing of emails for all doctors in the city to get their email addresses. But as it turns out, 9% of doctors in the city do not have a professional email address, and 25% of the doctors in the city are not on the internet email list because they've chosen to be unlisted. What percent of the doctors in the city have a chance of being emailed by Betty? So to be emailed by Betty, a person must A, have an email account, and B, be on the internet list. If we know the probability of these two events, we can multiply to find the probability of being emailed by dear old Betty. Okay, to be emailed by Betty, a doctor must have an email and be listed on the internet list. So let's take a look at the proportion or the probability of doctors who have an email. Well, we know that 9% of the doctors have no email, but we don't know how many actually do have an email. So we have to use the converse rule to find out 100% of the doctors minus the 9% with no email gives us 91% of doctors with email, and that equates to a probability of 0.91. So we know the probability of doctors having an email. But what is the probability that the doctors have opted to be on the email internet list? So we have 25% of the doctors who opted out of the email internet list. They have email, but they're not going to be listed. And 100% of the doctors minus the 25% who have opted out equals 75% of the doctors on the email internet list, or 0.75. So what I'd like you to do is take a moment to figure out the probability of a doctor being emailed by Betty. And if you need to pause the computer to compute this, go right ahead. Okay, you may have figured out that we need to use the multiplication rule because we're looking for two things in conjunction. We're looking for having an email and being on the internet list. We need those two conditions to be present. And so we're going to multiply 0.91 times 0.75 gives us 0.68. In other words, 68% of the doctors are primed for the picking from our salesperson, Betty. So now that you've taken some time to get to know these very basic rules of probability, tune into the next video to see how we use probability to find area under the normal curve.